So today is code optimization. So let's look at that. Oh, thought I had it running, but I guess not. All right, 142. There we go. All right. Okay, so we'll talk about what happens here. Now you have optimization flags in your compiler. And all the time we've just compiled with GCC without any flags, which is one way to do it, and perhaps the best general way to do it. Let me just set this up so I can see Twitch back there. I don't really need that. Be better. All right, so you have optimization 1, 2, and 3. 1 will do basic optimizations without slowing down the compile time. 2 will do some more optimizations, and 3 will do a lot, including ones that increase compile time. And this is the topic today, is what these optimizations do and when to use them. So here's things compilers already do. They fold constants, which means if you have a int debug equals n minus 5, and then you have here you define n to be 5, it will substitute this with 5 and then do the subtraction before it compiles. So it'll just start with int debug equals 0. So it does some calculation of these like macros before you even compile. And they do constant propagation. If you have a variable here, debug, but debug is set to 0 and never changed, it'll just put a literal 0 there instead of it being a variable because it knows. So that's another thing to do. That's constant propagation. And dead code elimination is another thing it can do. If you have a branch and it can tell the branch will never be followed, this is if 0 and 0 is false, so this will never happen. So it'll just remove the whole thing. There's no reason to even compile that code. It can tell it will never be executed. All right, it also simplifies expressions. Multiply and division are slow, so if you have a calculation 2 times an integer, it will just replace it with integer plus integer, which is just a faster way to get to the same point. And, all right, now the problem, the compiler can only do so much. For example, if you choose a bad algorithm, like bubble sort instead of quick sort, it can't fix that. It's not at all that smart. And, all right, and if you turn on these optimization flags, it might break your code. Sometimes the optimization is not accurate, and it changes the code's functionality. And one thing that's really a problem is whenever you optimize, you lose the ability to use the -G flag, so you can no longer do source code debugging. That's what the G flag allows. Because, of course, the source code no longer matches the compiled code. So you can't compile by lines of source code, and that makes it difficult to debug. So that's an issue. All right. Also, there's a lot of undefined behavior in C and C++. For example, if your a is the largest possible integer and you add 1 to it, it is not defined what it's going to do. It's an integer overflow. It might give you 0, it might give you 1 under different conditions. That's why they always say the technical word for this condition is undefined behavior. So it's very bad to write code that enters these undefined spaces and then imagine that you know what they're going to be. So pointers can lead to trouble. This one's a cute one. So I have a function here that takes in 2 pointers for a and b, and remember that if I pass in variables a and b, it'll pass in copies of the value, and whatever I do to those copies will not affect the original. But if I pass in pointers and then modify them, it will modify the variables in the calling routine. So if I pass in a and b, and then I multiply a by 10 and add b, that will have a certain effect if a and b are different. But if a and b were the same, then first I multiply a by 10, and when I add b, since b points to the same thing as a, I'll be adding 10 times the original a here, not 1. So if the compiler tries to optimize this to make this one line instead of 2, where it does a times 10 plus b, this is only accurate if a and b are different. If a and b are the same, this will get the wrong answer, because the b used here will be the a before it was multiplied by 10, and the b used here will be the a after it was multiplied by 10. So that's the kind of subtlety. So compilers will not make that optimization, since they can't assume that that's going to be true. All right, and so if you run this thing that calculates prime numbers, you can see if I just compile it different ways with no optimization at 6.5 seconds, this is 01, 02, and 03, and you can see each one of the optimizations does make it faster, until it gets almost twice as fast, 3 seconds instead of 6. All right, so optimizing. Code profiling is one way. Now, this is something people often do. They just decide to change the code to make it faster based on their own impressions about making code faster. And this, by your book goes against this. I think this is probably reasonable if you're a very experienced programmer and you can actually understand what's going to make it faster. But in general, you're likely to make false assumptions, so it's a better idea to actually measure the performance of your code. And you can do that here if you use time of day. So I can get the time of day and start it here, then get the time of day at the end and print the difference between them. So here it has a region where it allocates an array to store a bunch of numbers, and now it's going to calculate a bunch of prime numbers to fill it up. And in both of those, you get the time of day before and after, and then print them out. And you'll see allocating memory takes almost no time, just a few microseconds. Generating primes takes a lot of time, several seconds. So that's not a big surprise, but that's what you say. Therefore, the prime number calculation is what you need to optimize if you want to save time. So the gen prime sequence, which is what was called here, gen prime sequence, that calls gen next prime many times. Gen next prime calls is prime many times. So that's the code. So you have a loop here. This loop is good. This is inside is prime. It's going to go from 2 up to the square root of the number plus 1. It's going to check to see if it's divisible by any of them, and return 0 if it is, and otherwise return 1. This is one way to find prime numbers. It's a quite inefficient way to find prime numbers. There are mathematical tricks that are faster, but anyway, here's how it works. So you can then measure and see how this code is being used, and you can use that with this thing called call grind. You compile it, and then you run val grind with the tool equals call grind on it, and it will, I think it feeds in this number, just 100,000, so it has some work on, and therefore it will get 73 million events that it measures, and you can then use the call grind annotate tool to get the results. And the results will show you that square root here used 22% of all the time, and x% I used 22% of all the time, and those are by far the largest consumers. So now you know which part of it is using all the time. And so one move here is loop invariant code motion. If you think about this code right here, every time it does the loop, it's I equals 2, it then has to calculate the square root to see if it's at the end, then it does it, then it increments it, then it calculates square root again to see if it's at the end. It keeps calculating this square root once for every cycle of the loop, and there's no need for that. You could just move the square root out of there, like this, where it does the square root first and puts in a variable called max, and then it doesn't keep doing it over and over. And if you do that, you're going to save a lot of time. Like the time to generate is going to go from 2.4 seconds down to 1.4, so that's a large improvement. All right, that's moving static computation outside the loop. All right, one problem is, of course, you might not notice that something subtle is going on. It's possible that even though it looks like this number doesn't change, this might be a more complicated calculation that does depend on something in your loop, and therefore moving it outside the loop is not okay. So it requires the understanding of your programmer to know if that's going to work. All right, another optimization uses an assembly code square root function instead of a C library square root function. There are several math functions that are actually included in the processor, hardwired in, and those would be much faster. Modern processors even have AES encryption built right into the processor. So let's try a Kahoot. All right, so which optimization replaces some variables with constant values? That's constant propagation, a name that makes sense. All right, which process uses intuition instead of data? That's what they call premature optimization, where you guess what part of the code to modify to make it faster instead of first measuring to find out what part of the code is actually using up the time. All right, and how do you avoid repeating the same calculation many times? Take that invariant code and move it out of the loop so you don't bother calculating it over and over since it doesn't change. All right. So, all right, and I guess I'll get that other page back there a little bit better. All right, so other compiler optimizations you've got loop unrolling and function inlining. In general, you want to let the compiler perform the optimization rather than trying to do it yourself in source code. This is a big issue. I remember when I got a job at programming for a financial company, this was hard for me to learn. I was used to doing things in clever ways that were hard to read, and I learned to not do that. If you make code that's hard to read, it's very likely to lead to all kinds of trouble later, as either you misunderstand your own code, which happens a lot more than you might think, or whoever the next developer is can't understand it and gets it wrong. Usually writing code that is easy to understand is better than writing faster code that is hard to understand. It will lead to less trouble, and usually just paying for a little more compute time is cheaper than the consequences of having people misunderstand your code and make mistakes. Anyway, so here you replace, here's something you could do. You could call a function called allocate array, or you could just do it right here. And this is called function inlining, where you take the code in a function, and instead of being a separate function, you put it right in line. Now you'll save the overhead of calling a function, where it has to put things on the stack, make a separate stack frame and all that. But it does, of course, make your code harder to read. This is a general practice to make coding a general practice in coding is to write little functions that do one simple thing, test them, and then use a lot of little functions to do things. This way your code is easier to understand, easier to maintain, it's easier to reuse code as those little functions can be put again. So this sort of thing is what you do to make code clear, but this is what you do to make it fast, of course. You're going to save some time there. So that's an issue. That's called function inlining. And so you can suggest to GCC that functions should be inlined, and it will do that without the source code having to be inlined, which is the point. The compiler will figure it out for you. So you can write code like this that's easy to read, and the compiler will turn it into code like that that's faster to run. All right. All right, doing it yourself manually is very dangerous. I mean, one thing I know is if you do this kind of thing manually, and this function is called several places, you might not have exactly the same code in all those places, especially if you update it. You might not remember to update all those other places. That's why this kind of thing is easier to keep control of your code, although that might be faster. All right. So here's loop unrolling. This is a pretty clever trick. So here I'm going to go through from 2 up to the maximum, dividing by a number. So I'm going to have for every one of these values, I'm going to have to go back to here, increment the I, and compare it. Well, I could just increment by 2 and then do 2 comparisons in here. And then I'll have less of the overhead here, where I calculate whether the loop is done, and I skip ahead by 2. Now, one consequence is I might go further than I intended to since I'm going ahead by 2s. But if you don't care about that, then this would make it so your loop will be somewhat faster. It won't do this part as often. Of course, that part is probably not very expensive, but anyway, you do prevent some of the overhead there. That's loop unrolling. Branch predictors are a big issue in the world of security because of speculative execution. All modern processors do speculative execution. When they get to an if statement, they try to guess which way it's going to go, and they try to execute some code beyond the if statement. It may incorrectly guess when the loop is ending, so it wastes its time preparing to execute code that's not going to be executed. So loop unrolling means fewer loops and therefore fewer bad guesses for speculative execution. So a manual loop unrolling led to minimal improvement in your textbook, and when I did it here, I saw no improvement at all. So like they say, sticking to compiler flags is probably a lot better than trying to manually unroll loops in source code. All right, and then there's memory efficiency in addition to time efficiency. So here's matrix vector, and we did this one before in a previous chapter. This makes a big array, and then it fills it with I and J, allocates matrices, and then fills them with random data. All right. And time to allocate and fill. This looks like just a one-dimensional matrix. Matrix and result, and just fills them. Okay, fills this one with random numbers and fills that one with zeros. For rows, rows and columns. Okay. So it's going to do that in here. All right, the one I saw before had I and J, and I think it was whether you did it in the order IJ or in the order JI. This one here is confusing me. Time to matrix vector multiply. Anyway, it's going to compare various matrix operations anyway. And so what it's going to do is getting time of day and getting time of day. And this one gets time of day because here it gets time of day and prints time of day, time to allocate and fill matrices. Okay, so it allocates matrices and fills them with random numbers. Now it's going to fill array, get time of day, okay, time to allocate and fill matrices, then time to allocate a vector, then time to multiply a matrix times a vector. Okay, just various operations. You can see how long they take. All right. And so now we get to loop interchange. This is the one I was looking for, where we did this before. You have a two-dimensional array, and you either go through J and then I, or you go through I and then J. And although mathematically these end up in the same result, they're much different in efficiency because of caching. The one that accesses memory in order can load whole blocks of many integers at a time. The other one has to keep emptying the cache every time. So one of them is much slower than the other. And so the original, if you optimize it, you get almost nothing. The second one, if you optimize it, it will get much faster. And that's because, all right, it's smart enough to switch the order of the inner and outer loops. GCC does not do it by default, and programmers have to do it manually. All right, but with loop interchange, see this one here is slow, and it's slow in a way the optimizer can't fix because you keep going for like every 100th integer in an array, and then in every 100th integer again, and that just wastes a whole lot of time filling the cache and emptying the cache, and the compiler can't do anything. This one, you allocate all the bytes in order, so it can do all, and now the compiler, it's much faster in the first place, and the compiler can do things to speed it up, because this code doesn't have some huge inefficiency the compiler can't touch. All right, and other matrix filling is the next limitation. This one here, allocate to fill matrix. So here you are filling the matrix, and again, you're filling it with rows, filling all the columns again and again. And if you break the loops apart, here's another issue. It does two separate things. Fills this array with random and fills this array with zeros. If you break those into two separate loops, then a multi-core processor could do them both at once. If they're in one loop, then they can't. So that's another form of efficiency. All right, and of course, fill array with zeros is not needed. Apparently, when you first allocate memory, it is automatically filled with zeros. I'd have to look at the documentation to verify that, but that's another improvement. So if you want to see how memory is used, Massif is the tool that will do that. So once again, you run the program with some large numbers here, so it's got something to work on. You get the information the program provides, and then you can get a printout and shows you how much memory is being used by different routines, and it shows you that allocate array, which is here, uses 99% of all the memory, which is, of course, logical. That allocates that big array. All right, so, here's the standard thing. Use standard library functions, get evidence when you optimize your code, split your code into multiple functions, and worry about readability more than efficiency in writing your code. And let the compiler do automatic improvements is the best policy. All right, let's try 12b in the cahoots, which is here. All right, so what optimization is performed automatically at the highest level, O3? It's function inline. Let's go back to the slides and take a look at that. Yeah, see, that's it comes on at level 3. All right. All right, well, optimization improves the efficiency of speculative execution. That's loop unrolling, where you make it do fewer repetitions of the loop, so it has fewer chances to guess wrong about which direction the branch is going. All right, which one improves the efficiency of multi-core processors? Loop fission. Take a loop and break it up into multiple separate loops so it can run on separate processors.